Okay, let's dive into this. Welcome to today's Explainer, where we are looking at something truly awe-inspiring, the sheer, unbelievable scale of Earth's greatest giants. We're talking about creatures so massive they make buses, buildings, and sometimes even dinosaurs seem small. But we aren't just here to gawk at their size, right? We are taking a strict scientific look at extreme survival. We're going to explore exactly how creatures of this immense scale actually adapt, fuel themselves, and thrive in our world. And that brings us to the core question driving our entire explainer today. How do giants actually survive? Because think about it, extreme size requires extreme biological adaptations. You can't just scale up a regular animal and expect it to live. A massive body demands radical evolutionary solutions for hunting, for defending itself, for pumping blood, and honestly, even just for fighting the relentless pull of gravity. So this isn't just some simple countdown. This is a full investigation into the incredible, sometimes completely bizarre biological strategies that make gigantism possible. To really wrap our heads around this, we've organized these titans by their specific survival strategies. We'll be looking at masters of ambush predation, surviving Earth's harshest environments, marvels of biological engineering, the colossal filter feeders, and finally, some lessons from Earth's giants. All right, kicking things off with Section 1, Masters of Ambush Predation. You know, when you're a massive predator, chasing down agile prey just burns an unsustainable amount of energy. So what do? You master stealth. Take the Goliath bird eater, for example. With a leg span of nearly 30 centimeters, which is roughly the size of a dinner plate and weighing over 170 grams, it sustains its massive bulk via an ambush diet of insects, frogs, and rodents. But here's the catch. Being that big makes you a target. Rather than wasting precious energy fighting off threats, it employs a brilliant biological defense. It flicks these tiny, irritating hairs that embed right into a predator's eyes and respiratory tract. It's highly efficient, incredibly low-energy survival, and thankfully, it isn't deadly to humans. Now, comparing larger ambush predators reveals wildly different biological mechanics for the exact same goal. You've got the 250-kilogram green anaconda, which utilizes lethal camouflage and this slow, asphyxiating constriction. Contrast that pressure with the saltwater crocodile. At a whopping 1,000 kilograms, it relies on ancient, explosive kinetic energy, boasting the strongest bite force ever measured. So you're looking at sustained squeezing pressure on one hand versus instant bone-crushing power on the other. Let's move to Section 2 and see how this builds as we look at surviving Earth's harshest environments. Being a giant in a lush, prey-filled rainforest is one thing, but thriving in places where most life just straight up perishes, that is a biological miracle. Extreme environments absolutely force extreme biology. That 4-meter measurement, that's the dramatic leg span of the Japanese spider crab. To survive the crushing pressure and barren landscape of the deep sea, this thing operates in a remarkably slow, low-energy metabolic state, just efficiently scavenging the seabed. And this extreme efficiency actually allows some of these deep-sea giants to live for over a century. Extreme environments push anatomy to its absolute limits. What's really interesting about this is how, down in that same near-complete deep-sea darkness, the elusive 500-kilogram colossal squid evolved the largest known eyes in the entire animal kingdom. I mean, they act like massive biological satellite dishes to capture the absolute faintest bioluminescence or movement in a world without sunlight. And because we've only ever found a handful of complete specimens, researchers strongly suspect that even larger biological anomalies are just hiding out there in the abyss. Above the surface, the Arctic presents a totally different thermodynamic nightmare. To fuel a 700-kilogram warm-blooded animal in sub-zero temperatures, the 3-meter-tall polar bear requires a constant massive calorie intake. Brute strength just isn't enough in a frozen wasteland. They rely on an unparalleled, highly specialized olfactory system, capable of smelling a seal from over a kilometer away, right through thick layers of snow and ice. Their survival as the ultimate Arctic survivor is entirely predicated on this intense sensory adaptation. Moving right along to Section 3, Marvels of Biological Engineering. Water naturally supports mass, but being a giant on land, that requires staggering anatomical engineering just to fight gravity every single day. To get blood 6 meters straight up a giraffe's neck to its brain without it passing out, nature engineered an 11-kilogram, high-pressure, super pump of a heart. Then consider the 10-ton African bush elephant. To interact with its environment without wasting the immense energy required to constantly bend down, it utilizes a remarkably versatile trunk packed with 40,000 muscles. This gives it the fine motor control needed to hoist massive logs or delicately pluck just a single blade of grass. It's a true cause-and-effect biological marvel. But biological engineering isn't just physical. Sustaining a 10-ton body through droughts and harsh seasons requires a formidable neural network. The kings of the land possess staggering cognitive abilities, from recognizing themselves in mirrors to mapping and recalling specific water sources across literally decades. They are highly social creatures, even actively mourning their dead. Their survival relies just as much on these advanced, massive brains as it does on their immense physical frames. This brings us to Section 4, the colossal filter feeders. Now, this is the ultimate biological paradox. The very largest animals ever discovered in Earth's history fuel themselves almost exclusively on the tiniest organisms. The exponential jump in scale when an animal doesn't have to fight gravity is just jaw-dropping. Think about it. The largest land animal maxes out around 10 tons. The whale shark instantly doubles that at 20 tons. And then we hit the undisputed leviathans of the sea, the blue whale, rocketing to an incomprehensible 200 tons. Sustaining a 20-ton biological machine like the whale shark requires peak metabolic efficiency. Instead of expending energy actively chasing down large prey, this 18-meter giant just slowly cruises the oceans, passively filtering vast volumes of water to harvest tiny plankton. It's a completely harmless, low-output, high-yield survival strategy. And they peacefully swim right alongside divers, showing off these biologically unique spotted patterns that act exactly like human fingerprints. But honestly, absolutely nothing compares to the blue whale. The biological specs on this titan are just staggering. Over 30 meters long, 200 tons, a 180-kilogram heart, and a tongue that literally weighs as much as an entire elephant. And to fuel this impossible mass, it consumes several tons of tiny shrimp-like krill every single day. To coordinate and thrive in the vastness of the ocean, they generate these low-frequency calls that travel for hundreds of kilometers. It is the absolute pinnacle of giant evolution. And finally, Section 5, Lessons from Earth's Giants. So, I want to leave you with this provocative question to ponder. What do the existence of these giants actually tell us about the absolute limits of life on Earth? From those incredible low-energy metabolic states in the deep sea, to 40,000 muscle trunks, all the way to a 200-ton leviathan sustaining itself entirely on microscopic fuel. These extraordinary creatures completely redefine our understanding of what biology is capable of. They show us that life doesn't just adapt, it stretches the very boundaries of physics and chemistry to dominate every corner of this planet. Keep exploring, keep questioning, and I really hope this explainer left you fascinated and wanting to learn even more about the biological marvels we share our world with.